Imagine a train that never actually touches the track beneath it. No wheels gripping steel rails, no grinding friction, just a massive vehicle gliding forward as if it's floating on air. It sounds like something pulled straight out of science fiction. Yet this technology has been quietly operating in the real world for decades, pushing the limits of speed, smoothness, and engineering precision. So how do maglev trains work? And how is it even possible for something this heavy to stay suspended while moving at extreme speeds? That's exactly what we're exploring today, right here, on History of Simple Things. At the heart of every maglev train is the principle of magnetic levitation, using magnetic fields to lift the train above a track so it doesn't touch anything as it moves. Unlike conventional trains, which rely on metal wheels rolling against steel rails and create friction that limits speed and causes wear, maglev trains float a few centimeters above a guideway thanks to magnetic attraction and repulsion forces. Electromagnets, coils of wire that generate a magnetic field when electricity flows through them, are built into both the guideway and the train itself. By precisely controlling these magnetic fields, engineers create forces that lift the train off the track and keep it stable as it travels. This lack of physical contact eliminates rolling resistance and reduces wear and tear, enabling a smoother and potentially much faster ride than traditional rail systems. Maglev trains use two main ways to levitate: electromagnetic suspension, EMS, and electrodynamic suspension, EDS. EMS systems rely on strong electromagnets on the train that are attracted to metal coils in the guideway, lifting the train and holding it close to the track. Sensors constantly adjust the magnetic force to maintain a precise air gap. EDS systems, on the other hand, use superconducting magnets on the train to induce currents in the guideway, which generate repulsive forces that lift the train. EDS can lift the train higher and is more naturally stable, but usually requires the train to be moving before levitation kicks in, often meaning wheels are used at low speeds. Both approaches are effective and chosen depending on the system's design goals and speed requirements. Maglev trains are powered without wheels by linear motors, which act like unrolled electric motors embedded in the track. Coils in the guideway are energized in sequence to create a moving magnetic field, which pulls or pushes the train along. The train's magnets interact with this moving field, and speed is controlled by adjusting the frequency of the electrical current. Because there's no rolling contact, energy losses from friction are almost entirely eliminated, leaving air resistance as the main force slowing the train. This allows for smooth, rapid acceleration and very high top speeds that conventional trains cannot achieve. Maglev trains achieve extreme speeds because there's no wheel-to-rail friction to limit them. Experimental maglevs have exceeded 600 kilometers per hour, and commercial systems like Shanghai's routinely hit 400 kilometers per hour. With rolling resistance eliminated, most energy is used for propulsion, and careful aerodynamic design reduces air drag. Superconducting magnets in some systems generate very strong magnetic fields with minimal energy loss, allowing trains to maintain high speeds efficiently. These features combine to make maglev one of the fastest forms of ground transportation ever developed. Maglev trains are already operational in several countries. The Shanghai Maglev train has been running since 2004, connecting the city to Pudong Airport at speeds over 400 km per hour. Japan is building the Chuo Shinkansen, a superconducting maglev line promising record-breaking travel times between Tokyo, Nagoya, and Osaka. South Korea also operates shorter maglev routes, and China continues experimental projects to push speed and efficiency further. These examples prove that maglev technology is not just theoretical. It works in practice and continues to evolve globally. Maglev trains have several clear advantages over conventional rail. They offer quieter operation, lower maintenance for moving parts, high speeds, and a smoother ride because there's no wheel-on-rail contact. The lack of mechanical friction also means less wear on infrastructure and potentially longer system lifespans. However, these benefits come with challenges, especially cost and infrastructure requirements. Building maglev guideways is expensive because the entire route must be fitted with specialized magnetic systems rather than using existing rail lines. Energy usage at high speeds can be significant, and precise control systems are essential to maintain stable levitation. These factors have limited maglev expansion in many regions, despite the technology's performance advantages. Maglev trains represent one of the most impressive applications of magnetic and electrical engineering in modern transportation, using magnetic forces to lift and propel vehicles without touching the track. This technology reduces friction, increases potential speeds, and reduces mechanical wear, offering a vision of travel that feels futuristic yet real. From Japan's upcoming superconducting routes to China's high-speed services and beyond, maglev is already reshaping how we imagine fast, efficient land travel. Yet the hurdles of cost, infrastructure, and energy mean that while maglev will be transformative in certain corridors, it may not replace every conventional rail system. Still, by harnessing the timeless forces of magnetism to overcome physical limits, maglev trains remind us how far human ingenuity can push the boundaries of motion and connectivity. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.